Questions about anything from last time? Yeah, I'm running into an issue here today because it's crazy. Looks like I can't. You'll probably have a stupid thing to look at in the Boilercast. The camera's on and I can't turn it off, which means you're going to get a picture of the desk. Any questions? What? Any questions about anything from last time? Well, today I want to say some more things about the complex exponential. And this will be the last day where I write e to the x plus iy for the complex exponential. After today, I'm going to write e to the x plus y for it. Anyway, the properties I showed you last time using trig and facts from calculus are there. The big ones are that the complex exponential is its own derivative, and that formula number 3 there is a very important thing. And I wanted to think a little bit more about this from a complex calculus point of view. So a little lemma is going to come in handy today. If f is analytic on C, or a disk, if you want to, it works on a disk too, but I might as well assume it's analytic on the whole complex plane, and it satisfies this differential property that f prime of z is equal to a constant times f of z. Then there's only one thing f could be. Yeah, the exponential, I heard it. You've studied that differential equation in freshman calculus. That's derivative of something, dy dx equals k dy. Dy dx equals ky. You know that the solution to that differential equation is the exponential function e to the kx. And that's exactly what's going to happen here. F of z has to be the complex exponential function. And k could be a complex constant here, but what did I say? K. Yeah, K. Then, where? Oops, that's not right. Something to add here. Let me move this. C times e to the kz, where C is equal to f of 0. That's a classic differential equation you learn how to solve. You learn it in freshman calculus, and then you may take something like Math 262 and learn it again. Well, the y here is basically a Math 262 thing. So if you look at this equation here and think of it as a differential equation, that becomes f prime minus kf equals 0. That's a first-order linear equation with constant coefficients. First-order linear. It's an ODE in the complex domain. ODE in C with constant coefficients. You learned how to solve those in Math 262. Integrating factor, that was the trick. Multiplying by an integrating factor makes it the derivative of something. And the integrating factor in this case would be e to the k x in Math 262. So the big idea here is we know Math 262. We're not sure it's going to work the same in the complex case. Let's multiply the ODE by what we think the integrating factor ought to be. In this case, it would, let's see, what is it? It's e to the minus kx. That's the integrating factor. E to the minus kx. And so I'm going to multiply by the integrating factor e of minus kz. When I do that, I get e of minus kz times f prime of z minus k times e to the minus kz times f of z. That needs to be 0. And sure enough, that's going to be the derivative of something. So in fact, let's see, I claim that that's going to be the derivative of, this is what it's supposed to be, d by dz of e to the minus kz times f of z. That's kind of a question mark. And the question is it? And the answer is yes, of course. Because d by dz, we learned the chain rule last time, or at least we learned it before, but we saw a proof last time. D by dz of e to the minus kz would be e prime of minus kz times d by dz of minus kz. And e prime is itself, remember. We know that. So that's e to the minus kz. And then here times minus k. And that's exactly what we have in the product rule for differentiation. First I differentiate f in the first piece there. And then I differentiate the e to the minus kz in the second place. And I get the minus k, this thing right here. That's what I get, times f. And so sure enough, that's the product rule. Question? Oops, you're right. The derivative is itself. I know that. That's how we cooked it up last time. Okay, so that means that that thing is identically 0. So this derivative is identically 0. That means, remember the thing I proved last time also, is that if the derivative of a function is 0, it's constant. So we conclude that e to the minus kz times f of z is a constant. And we see what that constant is by plugging in z equals 0. We plug in z equals 0. We would see that that constant is equal to f of 0. Because remember, e to the 0 is 1. Okay, so now here's something kind of weird and sneaky I'm going to do. I'd like to be done at this point. I'd like to use the fact that e to the minus kz is 1 over e to the kz. And then I'd put that on the other side and be done. But I want to do everything from first principles today, so I'm not going to assume I know that yet. So here's something sneaky I can do. Stop at the proof. Start over. But this time, that f of z, use that f of z is equal to e to the kz. Let me put this in a big red box. That's what we deduced from so far. And if I let f of z be e to the kz, notice that f prime of z by the chain rule would be e prime of kz times d by dz of kz, and that's k times e to the kz. K times e to the k times z. That means that f satisfies, let's see, that's equal to k times f of z. So this f satisfies the hypothesis of the lemma. F of z satisfies the hypothesis of the lemma. So we could have started over and get to that red box. The red box says, what does it say? E to the minus kz times f is a constant. The red box would say e to the minus kz times the f, and f, this time I'm taking to be e to the plus kz, is a constant. And that c is equal to, let's see, that c would be e to the k times 0 equals 1. So in this red stuff, so I just showed those have to be non-zero. Those two are non-zero, and they're inverse to each other. And e to the minus kz is 1 over e to the kz. Okay, now I restart the proof. Back to proof with my original f of z, which I don't know what the heck it is. That red box now I can use my fact that I just showed that e to the minus k of z is 1 over e to the kc. It shows that f of z is c times e to the kz, which is what I wanted to see. And I noticed before that c is equal to f of 0. So check. That's the demonstration. So I demonstrated that some of those facts from calculus ideas, Math 262 ideas. They work just fine in the complex domain. And now I want to do one of my favorite things. So I call, this is something very cool. Let's let f of z be equal to e to the z plus w. I'm going to use this lemma now. Any questions, by the way, about anything? Where think of w as a constant. Then f prime of z would be e prime of z plus w times d by dz of z plus w, but w is a constant, so that would be 1. So that's equal to e to the z plus w, which is our f of z. So that f of z satisfies the hypothesis of the lemma with k equals 1. So it satisfies a hypothesis of the lemma with k equals 1. So that means that f of z is equal to a constant times e to the 1 times z, where c equals f of 0. That's fascinating. So remember what f was. F is e to the z plus w. C is f of 0. So that c is going to be e to the 0 plus w. That's the c. And the lemma tells us that this is going to be e to the 1 times z. And so we see, aha, I've just deduced that formula. E to the z plus w is e to the z times e to the w. That's cool. That means I can deduce truckloads of trig identities, and all I used was calculus. I've never drawn a triangle. So I used trig identities to prove these facts the first time I saw them, but now I've used calculus to deduce these facts, and that means I can deduce all those trig identities, starting from complex analysis. Deduce truckloads of trig identities without drawing a single triangle. That's kind of cool. Okay, so now this is the moment I'm going to stop writing e of z and I'll start writing e to the z. So let's think about the graph of e to the z now that we've got it in our hands. We're in 2 dimensions now, so that's kind of a wonder how we're going to do this. I like to think of e to the z on horizontal lines. That's the easiest way to visualize it. So here's the complex plane. I'll take a horizontal line. I think I prefer orange for these horizontal lines. Okay, so I'll make this point be a y here. And so these points along here are x plus iy. So we can think about where this thing goes. I'm going to use a convention of a single arrow to the right of the y-axis, and I'm going to use a double arrow here for the line to the left of the y-axis. So of course this is the x-axis, this is the y-axis. Well, that e to the x plus y is e to the x times e to the iy. Okay, and x is going from minus infinity to plus infinity. So minus infinity is less than x is less than plus infinity. So e to the x, we know what the real exponential does. E to the x is going to go to infinity on the right, but e to the minus infinity goes to 0. And so as that x plus iy traces out that orange line, it's going to get mapped over to this orange line. Okay? And at radius r equals 1, that's where x is equal to 0. That would be e to the 0. So this, we see this is e to the x is the radius here. And y is equal to the angle in the polar form of a complex number. So let's see, that case is when x is equal to 0, that's on the y-axis there. That means the orange stuff to the left, the double arrow stuff, gets mapped to this part of the radius, and the stuff to the right gets mapped to the radius outside r equals 1. And this angle here is y. Okay? That turns out, if you understand that well, that means you understand the complex exponential. It's kind of a beautiful picture to think about. So let's see, if I take a region here, I'll use purple for the, I'm going to let the horizontal lines go from the axis here and then up. I'm going to go up to I pi. We'll make that line green. Okay. And I take these horizontal lines like that. The orange, the purple one, theta equals 0. This is 0 right here. That's y equals 0, so that angle would be 0. That purple line, if I wanted to, I could put double arrows over here. That purple line is going to go to the positive real axis. So here's 0. And if we cared, here's 1. The purple line would, to the left would get squeezed and squished down into that stuff from 0 to 1, etc. And then that orange lines would radiate around here. And when I get to pi, the green line would get mapped to, let's see, the minus 1 would be the new spot where, like that. Interesting case here. If I made, what's a weird color? Blue. This imaginary axis thing, that would be e to the 0 times e to the iy. That imaginary axis thing goes around like this. That's the unit circle. And it goes from angle 0 to angle pi. Okay? And if I cared about double arrows, I'd have single arrows outside the blue circle and double arrows inside. But what's fascinating is that that is a one-to-one onto map. So going this way is e to the z. And then you think about, the inverse of that map should be a complex logarithm. And in fact, it is. And that's going to be an analytic function. And it's going to be the beginning of the complex log function. So let me summarize this in a fact. Fact. E to the z maps that little, let's say I want to make a domain. So I want my domain to be an open set. So I'm not going to include the orange, I'm not going to include the purple or the green lines. E to the z maps the z such that 0 is less than the imaginary part of z is less than pi. That's an open set. It's connected, so that's a domain. One-to-one onto. There's exactly one point that gets mapped to each point. One-to-one onto the upper half plane. Okay, I like to write upper half plane. And I'll only write that once. I call that the UHP for upper half plane. Upper half plane, which is the z such that the imaginary z is positive. Notice that I'm not including the real axis there. Okay, well, I did that slowly this time. Now I'm going to blast through and do e to the z everywhere. Questions so far? It's good to get comfortable with complex exponential because the complex log function is a wild, kind of a wild object. It's not so wild when you look at it in pictures here, so the pictures are going to be an important way to understand these things. So let's see, I'm going to keep up with my purple and green business. I'll have purple is the real axis. Let's see, I'll do it, maybe I can do it all at once. Purple. Purple. Green. Green. That might be too much. Okay, so here's 0. Here's I pi. Here's I 2 pi. I 3 pi, etc. Here's minus I pi. Minus I 2 pi. And minus I 3 pi. And now, remember those purple things go to the positive real axis. Interesting, 0 never gets hit. And the green stuff all get mapped to the negative real axis. Okay, and I'll stick with my colors. I made this orange last time. That orange stuff got mapped to the upper half plane, one-to-one and onto. I could do the same thing with the negative angles there. Let's see, what color should I make those yellow? Do they show up? Anyway, can you see those yellow things? The yellow is just not orange. These are all going to map to the lower half plane. So it's like a American flag stripes kind of thing. The orange stuff all gets mapped to one-to-one onto the upper half plane. And the yellow stuff all gets mapped one-to-one onto the lower half plane. And 0 never gets hit. So e to the z is going this way. If you're going to think, oh, you know, on the real line, we were able to define the log function for all positive real numbers. But now we realize, oh my gosh, I can come up with a log function for every complex number there except 0. But the problem is, I have a choice to make. In the real case, there was only one choice of a log. There was only one y so that e to the y was equal to x. So it was uniquely determined. Now I've got to choose. So if I have a point, say right here, there's a w. If I want to find the log of w, I realize, oh my gosh, there's one in each of these orange strips. I got to pick one. So that's what we're going to start thinking about. From a global perspective. Well, there's the principal branch of the log that I will define in a second. In the principal branch, I want to pick exactly one thing that and fill out the whole complex plane that way. So let's think about, this is the principal branch. Maybe I should use green. I think I'll use blue this time. Blue and green. And this time I'll put up here I pi, and the blue line is going to be at going through minus I pi. That's going to make the angle go from minus pi to plus pi. And you remember the principal argument was relevant for that when we were dealing with minus pi and plus pi. And so now I'm going to use orange still to shade the region here. Now if you think about what happens here, e to the z, it's going to map both those lines, the blue one and the green one, are both going to get mapped to the negative real axis. Okay? And if you think about it, well, 0 never gets hit. And you think about the negative real axis, if I don't include those in my boundary of my domain, then I don't have to worry about where those two go. But they both go to the negative real axis. And all the rest of that stuff maps one-to-one onto the whole complex plane minus that little red branch cut. So that red thing is called a branch cut. And I like to think of, think about this. Think about opening a fan. Okay. Remember those horizontal lines go to radial things. So it's kind of like opening a fan, and this part of the fan opens out and connects here when I open the fan as far as it goes and let it connect. Okay. And this part of the fan, when I open it up, that's heading toward minus pi angle, and so it's going to fill out this part. Okay, this is the principal log. And I like to write that capital L-O-G-W. I use capital L like I use capital A for principal argument. That's the principal branch of log. And we get the first time I mentioned branch cut on purpose. I've said it by accident, maybe. Principal branch of the complex logarithm. Okay, and let's think about how we're going to... I'm going to tell you what that is. But note the way e to the z maps that strip, that's z, such that minus pi is less than or equal to, the imaginary part of z is less than or equal to pi. one-to-one onto C minus this branch cut, and up. The 0 is the endpoint there. That's not in the domain either. That's yanked out, connected to the branch cut. And log is its inverse. The principal branch is its inverse. And there's an inverse function for analytic functions. The inverse of an analytic function is analytic. That's a fantastic thing. Question? Oops, that's a less than. This is a domain. Thank you for catching that. Yeah, you're right. That didn't belong there. In fact, we're going to think about who's going to win on the pi, minus pi lines. Because we'd really like for every complex number to have a unique log. And in this picture, everything but the red stuff there has a unique log. And if you think like a computer programmer or engineer, you want to define the function even on that stupid red line. Okay, so let's think about logs for a second. Let's write W equals e to the z. That's equal to e to the x times e to the iy. Okay, that's an r e to the I theta. So this is e to the x is the r, and this is the e to the I theta. And let's see, the r is the modulus of w, the radius, and let's see, it's also equal to e to the x. So x is the natural log of the modulus of w. No choice. The real part of a complex log is determined. But it's the argument that's going to lead to something we've got to think about. So, important thing, x has to be the natural log of w. And we see that the theta, the y, remember I used a set. That's in that set of arguments of z. Okay, there's lots of arguments of z. That's a set of theta such that w equals r e to the I theta. I'm sorry, the argument of w, yeah. R has to be the modulus of w. Okay, so choosing a log function is strictly choosing an argument. That's all there is to it. So we're going to write z is a log of w. The real part has to be the log of modulus of w, and the imaginary part is plus I theta, where theta is an argument of z. What did I say? W equals e to the z log of w. Theta, right. Okay, so here's my notation and my definitions. My notations. And definitions. Ln is reserved for real positive numbers. The real log, natural log. And of course, that's a function on R plus. It bugs me when people write ln and they're talking about a complex logarithm. And it's amazing how many people are going to end up doing that and bugging me. Okay, and here's my other notation. I use, like I did for little arg, I use log of w to be the set of all possible logs. So that's the z such that e to the z equals w. And we've seen that that's equal to the natural log of w mod w plus I theta, where theta is an argument of z. Okay, if you want to think about all the possible arguments, that's equal to the set of log mod w plus I times theta, where theta is the principal argument of w plus some multiple of 2 pi, n times 2 pi, such that n is an integer. Oops, this is arg w. Dumb. This is the principal argument. And my other notation that I'm picky about is when I say log with a capital L, I mean the principal log. And that's going to be, the real part has to be the log of the modulus of w, but then I'm going to take the principal argument of w here. And that means I'm choosing a winner in this argument. This is minus pi is less than the principal argument of w, and then at the pi side, we let pi win. That way, everything in the complex plane has a complex log, except the origin, 0. Questions about anything? And here's my other notation that it appears in some books, but not all books. If I let my angle go from, let's see, I want my angle to start at alpha. And then if it starts at alpha, I'm going to let it go to alpha plus 2 pi. And then I think about what's going to happen to that under the complex exponential. E to the z would map that. Let's see, the line e to the I alpha is a thing like this. This would be angle alpha. And let's see, I'd start with radial lines at that angle alpha and go all the way around to alpha plus 2 pi. So, that would be a 1-to-1 onto map of that horizontal strip onto the complex plane minus that red line. That's the branch cut. And I like to call this script. This is a branch of the log function. This red line is a branch cut. And this is a branch that I just defined. This is called a branch of log. And I like to make that sub alpha to emphasize that the angle is going to go from alpha to alpha plus 2 pi. And so my definition for the rest of the course is going to be log alpha of w is equal to the natural log of mod w plus I times theta, where I choose the argument. It's the argument of w, but I choose the argument to be less than alpha. I'm sorry, alpha. The argument's between alpha and alpha plus 2 pi. And I don't care about who wins at the ends, because I'm looking for an analytic function on the open set there. Questions about that? Let's see. A popular branch that we'll use from time to time. There's the principal branch, which has the branch cut going out the negative real axis. A popular branch would have it going out. Let's see, I'm going to take here 0 and I times 2 pi. The complex exponential maps that. Let's see, so those get mapped to the positive real axis. And it maps the complex plane minus that slit, branch cut, 1-to-1. It maps 1-to-1 onto that. And then this going the other way would be the branch I called log 0 of w, where the angle would go from 0 to 2 pi. That's 1-to-1 onto. So you see, the complex case is way more involved than dealing with the real exponential. The real exponential goes like this. It's 1 there, and then it shoots up. That's e to the z. That's e to the x, rather. If I put an x here, there's exactly 1 y. So that e to the x is equal to y. Only 1 y with e to the x equal y. So we define it, y as the natural log of x. And that's simple. That's only defined on the for positive real numbers. The great thing about the complex exponential, it's defined for any